in this period of my life, I cannot see nearly anything. So be patient. I try to place in the right distance. Okay. Okay, so I will try to give you a different viewpoint on continuum mechanics, and I will try also to prove that it is not true that old means boring. I will try also not to overlap too much with the lectures which Pierre Seprecher will present to you. But you know, we met, it is a shame, we met something like 25 or 26 years ago, and we are still working together. People say that I am somebody who is easily upset, but to my memory I never quarreled with Pierre, so maybe it is fault of other people. If you are loyal, I will never quarrel. Okay? Okay. So, why I wanted to tell you, I was very young when I met Pierre Seprecher, and we had written 2 theses. If you go to the internet, you could change the name. The style is different, notation is different. But if you talk about the contents, you could, and nobody tells you who wrote what, you could mix the two. However, there is a fundamental difference between them. The fundamental difference is that Pierre's thesis is based on the principle of virtual work, while my thesis is based on principle of balance of everything. Balance of everything, which is important. I am not ashamed to say that the provincial School of Mechanics of Napoli, who on the other side has always been very advanced, in that period was fond of the American school. When we are not video recorded, I will let you hear a beautiful song by Renato Carosone, whose title is Tu vuoi fa l'americano? You want to be American. You know, people like very much to be trendy and to follow the American style. Okay? Now, this is a big shame because continuum mechanics has been invented by an Italian scientist whose name is Gabriel Piola. And it is a big shame that Italians forgot this. Okay? Of course, Gabriel Piola was pupil of another famous Italian, Lagrange. He was Lagrangia, but he decided to become French. Okay, so thanks to Samuel, we have already spoken about this, but there is another Italian. You know, this is beautiful. The Italian of Leonardo da Vinci is very elegant, but here you have the translation in English. Even if it has been said that mathematics which I'm using is uselessly foggy, I think that in order to understand complexity, you need complex mathematics. Now we have time and you are young, and you don't have straight jackets. Your brain is free. So I will try to persuade you that the point of view which we have, by the way, inherited by Gabriel Piola, is the right one. This is the website of M&MoCS, but there will be occasion to talk about M&MoCS, which is inspired by the idea of trying to support the central role of mathematics in every scientific endeavor. You know, mathematics is a difficult subject. You can resume in this way: the mathematics which I know is good and useful, the mathematics which you know is useless and too abstract for being understood. This is the standard rule. Okay. Mathematics is needed in order to get logical deduction from hypotheses. Of course, if your hypotheses are wrong, you get correctly deduced wrong results. Moreover, ex absurdo omnia secuntur. If your hypotheses are contradictory, you can prove everything. So you have to be very careful in using mathematics. In this, I agree. Now, why I'm telling you this? You must be patient, and before looking with me to the applications, you must review, and I will give you all details, all documents, all references which is needed. You must review with me a little bit of differential geometry, and I'm sure that I can explain in an understandable way what I want to say. But in any case, do we want to study a cube, and in particular the geometry of a cube? I mean, nobody, even in these days, nobody can claim that a cube is a useless object. Okay. Now, a cube is very tricky and sometimes very bad because it has edges and wedges. So, when you integrate by parts on a cube, you have troubles. Okay? Now, what is interesting is that this, with Pierre, we have found some years ago a book written by two mathematicians. I don't know if they are like brother Cosserats or not. They introduced the concept of piece with boundary smooth manifold. And now I try to give you an example. No, it's not piecewise. They call it piece with boundary, smooth. Okay, this is, of course, the names, you can play with them. Okay, so we start slowly. Usually when I do presentations, I must either pretend that this is obvious, or I must tell it very quickly because these boring details are not well considered. Okay, you will see in 1 hour, I think, that you need to integrate by parts in order to get some interesting informations about boundary conditions in generalized continua. This is the general frame. Where you can integrate by parts? You need boundaries having reasonably smooth boundaries. Okay? Now, I'm sure that you can do this integration by parts in more general setting. Maybe even if you have a boundary which is a fractal set. I don't know. I don't want to know. What I want to tell you is that for a particular class of surfaces, the process of integration by parts which I will perform is possible. Then it is an open problem to establish for which other families we are able to do the same. Okay, so this is not limiting the theory. A theory whatsoever will need to talk about contact actions on a cube. This cannot be discussed. So in order to understand which boundary conditions you can apply on a cube, you need to learn how to integrate by parts on a cube. Okay. Now, we try, the pictures I've shown you, and you can see in every general screen, are polyedra. So we have in mind a generalized, slightly generalized set of shapes. We need a surface. We call it piecewise regular. It is also orientable. You have a normal everywhere or nearly everywhere, and it has to be rectifiable. You need to calculate integrals on it. Okay? It is embedded in E3, and then, so we are in the realm of Gaussian geometry. Okay? We have embedded surfaces in E3, so something which we can even believe we touch and see. Okay? Then you assume that you have a finite set of curves which are C1. These curves are included in this surface. Okay? And a finite set of points which we call wedges. And we assume that we need to introduce the concept of generalized boundary. The boundary of this surface is the union of all these curves and the border or the boundary. There is also, the theory is not well rooted enough, so you don't have a unique denotation in the literature. And then you have the double boundary of S, which is the new union of the points. You have to be careful because in Poincaré theory, the boundary of the boundary is empty. Because in Poincaré theory, you assume regular, very regular surfaces and very regular fields. Okay, so you have a surface, you have a finite number of curves, and you have a finite number of points. I call, for the moment, it is a name. I call boundary of this surface. The support of the boundary of this surface is a set of points, which is the union of these curves. And then I have the boundary of the boundary, and this is a set of points. Okay? So I think that up to now I have not said anything too much difficult. Okay, so for every point in the surface which is not in the boundary or in the double boundary, okay, you have a chart. So you have a set of coordinates in this neighborhood, and these coordinates are one-to-one labeling every point in this neighborhood. So you have a chart in the Levi-Civita sense, okay, in the sense of differential geometry, standard differential geometry. Okay? Okay. Then you assume that in every internal point of this surface, the internal points are the points on the surface which are not in the two boundaries, you have a vector which you call the normal to the surface. And this normal is orthogonal to every tangent vector to the surface. So this is standard geometry. Then you have border charts. So when you are on one edge, you have two sides of the edge. So you have like a half circle on one side, half circle on the other side. And these half circles are diffeomorphic to circles in R2. Okay, so you have what is called a boundary chart or border charts. Okay, you have these for R plus and R minus. Then you have the parametric no, sorry, I have to say also this. Then on both sides of every point on an edge, you have the limit from plus side and minus side of the normals. So you have well-defined normals for every face, and you have a well-defined limit of the normal in every point of the edge, okay, of each of these curves. And these two normals may be different. So you have n, capital N plus and capital N minus. Okay. All this is needed if you want to describe what is happening here. So this is an internal point, this is an edge, here you have a point in the edge, okay? Every curve is C1, you have a tangent vector to the curve, and the tangent vector of each of these curves is orthogonal to the normals on both sides. If somebody heard about Frenet trihedron, n plus, n minus, and the tangent vector to the curve are not the Frenet trihedron. Pierre was worried. I'm not so senile. Okay. We discussed many hours about this. So this trihedron is intrinsic to the surface and its edges, not intrinsic to the curve. The trihedron, Frenet trihedron of the curve is different from this geometric new object, which characterizes the shape of this surface in the neighborhood of any point in the edge. Okay, so if you want to go into bigger details about this, we will talk in the afternoon. We'll talk whenever you want, because these concepts are not so difficult. My generation was obliged to study these things when we were 19 years old. I don't know what happened next. People now retired did a lot of damage. We will try to repair to this damage. Okay. And be careful, in every point of the edge, you have the normal n plus, the tangent vector to the curve. You calculate the vector product of these two vectors, and you get the outer normal to the curve, which is tangent to the plus side of this surface. When you have studied Maxwell equations, this normal played a role in Ampere-Faraday laws. Okay, and you have two of these outer normals, which are outer normals to the curve in the tangent plane of one face. And this plays a crucial role in the integration by part process, which I will present you. Then every curve has a starting point and an ending point. The starting point is one wedge, and the ending point is another wedge. So we assume that these curves are concurring in a wedge. Okay? We can most likely do something with a pinnacle like a cone having a wedge without any concurring curve. But we need young people for doing calculations with us. Okay? We need to understand a lot of things. Maybe this is easy, but to generalize this process, we need stronger people. By the way, this paper, I think we started in '95. And we are still producing something more or less periodically on this. Okay, So, roughly speaking, piecewise regular, orientable, and rectifiable surfaces, in the conventional sense which we have specified, are surfaces where the normal is defined in all points except those belonging to a finite set of wedges and to a finite set of regular curves, which are the edges of the surface. By the way, in one wedge, you have a limit of normals coming from all faces which are concurring there. Okay? So now the complexity of the geometric object should be clear. Okay? And so, following the trick, rhetoric trick by Demosthenes, now we relax a little bit talking about phenomena. And, you know, Pierre is not as a good boy as he claimed to be, because he has written 2 beautiful papers without me, and I'm obliged to say that they are very good, and to tell why they are very good. My dear young friends, you know, it is clear that I will not get Nobel Prize, but at least I want to try to send a strong message for young generations. In your life, you should get rid always of any conceptual straitjacket. You know, there are people, like the Jesuits, who refused to look in that devil instrument used by Galileo to see the sun, because they were afraid of looking something which was outside their mental construction. You know, our brain is very good. We build beautiful constructions, but reality is reality. If it is not fitting our mental construction, we must change, not the reality. You can burn Giordano Bruno simply because he said there are many stars. And in your mental construction, there is only one star. Okay? The stars would remain there. Now, the battle which with Samuel we are fighting with different styles, because Samuel is less polemical than me, okay, is this one. Cauchy gave us a wonderful continuum theory. It is very effective, but it is not applicable always, in every situation, for describing any kind of phenomenon. Okay? So, the school, especially Truesdellian one, because you know, you must also distinguish between Aristoteles and Aristotelians. Aristotelians are sometimes much worse than Aristotle himself. Okay? So, why this forward? In the beautiful papers by Pierre Seppecher and his co-workers, it is proven that when you start with a Cauchy continuum at micro level and you play in a clever way with the stiffnesses, the geometry at micro level, and then you have a small parameter epsilon which tends to 0. Some stiffness goes to infinity with a given speed. Some geometrical property goes in another way. So if you have multi-scale, microscopically complex, strongly dishomogeneous systems, the limit which you get at macroscopic level is not a Cauchy continuum. So if you want to describe at macroscopic level complex systems, you cannot limit yourself to Cauchy continua. Now, what is astonishing is that before Pierre, and some papers I wrote, some papers written by Samuel and so on, you find this written in Gabriel Piola's book, written 1848. Okay? So, mathematicians knew it, but this has been forgotten. So, the ancient problem is modeling complexity at micro level and at macro level. Then there is also another challenge we need to discuss. Natural materials are those materials which the standard physical forces produced for us, and we get more or less already ready, even if a piece of metal is not already ready in the shape of a blade. You need to melt and do some hammering and so on. But anyway, nowadays we want to invent metamaterials. We want to invent materials which are not already existing. And how do we invent metamaterials? Usually we write the equations and then we look for something which is governed by these equations. So people telling that mathematics is not important should think about this. Mathematics is shaping our world in this sense. Another thing I must and I won't tell you, stress and strain, in the sense I am also teaching, we are teaching to students, are concepts which need to be generalized. The way in which we are teaching stress and strain is suitable for Cauchy models. It is not suitable for more general continua. So generalized continua require the introduction of a more general concept of stress and strain. Okay. Of course, when we will have a more powerful tool in our hands, engineering applications will arrive. But I want to tell to the industrial participant of this conference that usually between the moment in which you conceive a theory, Newton's calculations for throwing a satellite outside Earth attraction, and the moment when you build a rocket, you have some time in between, okay, and generally it's not tomorrow. People working at the university, paid by the state, are working for future, okay? The satellite which arrived in the last days to Pluto has been designed with the laws conceived by Laplace under the orders of Napoleon III. If you stop now studying mathematics, in 3 generations we will be in serious troubles. Okay? So we are a little bit like monks. We will go to a monastery where knowledge of ancient Greeks was preserved during the millennia of Dark Ages to reach Galileo. Okay? So we must also be ready to do these things, studying a theory in a very detailed way and then pretending that we are doing something which can be applied tomorrow. We will do a small estimate of the times, and it will be applicable in 50 years maybe. Okay? Now, let us look. Pierre also worked with Milton Greme. Milton Greme invented a material which has been printed in 3D with a 3D printer, which is not able in the reference configuration to exert shear. They called it pentamaterial. This is a bichiral metamaterial I must thank Nicolas Offray for having attracted my attention to this. The symmetry group of this material at macro level implies that at macro level this cannot be a Cauchy material in some sense. Look, this, if you studied a little bit the genesis of Lamé coefficients, there was a long discussion in the French school if you could have a negative Poisson ratio. Now, if you look at this bar here, if you pull it from this side and the other side, this bar becomes strident, and the other bar moves up, and macroscopically you get a negative Poisson effect. So this is a typical metamaterial, something which has been conceived for doing something exotic, for having an exotic behavior. Okay? This is a famous pantographic plate which we will discuss, and was the object of a paper with Jean-Jacques Alibert and Pierre. In this moment we built a pantographic sheet. I will describe you in more details. I'm working not only with Pierre with this, but also with Claude. It is a set of, I sometimes exaggerate in joking, but I think that even if it is not popular, South Italians are Greeks. We are Greek from Magna Graecia, and we use all rhetoric tricks of Greek tradition. To make something unforgettable, you must associate it to a joke or to something exaggerated. Okay? So I try to exaggerate. Moses, in the tables of laws, wrote, "You, engineer, will never use pivots inside a structure. And if you use pivots, they will be only at the end point of beams." I worked with Massimo one day looking for the way for introducing a pivot. You have a beam here, another beam here, and a pivot connecting them this way. It is not easy. Maybe it is possible, but you must suffer a lot of time. So we decided to start a new code with Mathematica and do the job in a different way. This specimen is made of beams, 2 orders of beams. One beam is in this, one family of beams. This is one beam starting from here, ending there, and the other in the other side. Okay? I will discuss with you in some detail the behavior, the mechanical behavior of this pantographic structure. What happens is that you have a floppy mode locally, no energy, or only the energy related to the rotation of the pivot, if the 2 beams are doing this. Okay? So you have an elongation which is not costing a lot of energy. So if you want to conceive a material which is very good in resisting to traction, large tractions, without being broken, this could be a very good idea. And indeed, it is used in many composite materials. Okay, the good news for us is that if you want to study this animal, you need, with a continuum model, you need second gradient energies. So you need higher gradient theories. But you know, complexity is also natural. The group which is studying porous media with flow inside and this. By the way, this is not a coral, this is a metallic foam. I used this picture because, you know, structure is very attractive. This one is the internal, another kind of aluminum foam. This is the internal part of bone, and this is the schematic distribution of water, air, and solid grains in a porous medium. This is the complicated way in which a fluid is flowing in a... Look, what you have in common among all these pictures. You have empty space, very strong material, weak material, a solid, a fluid. The solid can exert shear, the fluid cannot exert shear in equilibrium at least. Then you have capillarity phenomena, so you have already second gradient energy playing at the interfaces between different fluids. So you have what we can call strongly, this is concrete. In Grenoble there is a group who claims that also concrete is a second gradient material because of the high inhomogeneity which is showing. For sure, for describing dissipation in concrete, you need a microstructural parameter, and also salt cavities in salt. Salt is also a material which is strongly inhomogeneous. Okay, this picture in the center, you have, on the right you recognize me, in the center you have Richard Tupin, the loser of the battle about postulation of continuum mechanics of the previous generation. He is a variational man, and he repeated at this dinner, I think at least 20 times, I believed this man is really senile. He's gone. I needed some time for understanding what he wanted to tell me and what he wanted me to repeat. Mathematics is the art. Imagine an old man, more than 85. Mathematics is the art of giving the same name to different things, unifying concepts. Okay? Henri Poincaré said this, so French people should approve it immediately. Okay? Actually, Richard Tupin said,
why do you say that he was a loser?
I will tell you. Richard Tupin was the champion of variational principles, and he lost against Knoll, the champion of balance of everything. Okay? And of course it is not polite, so I will not give you the list of names he gave to me about people having the habit of giving different names to the same thing in order to write more papers. But he warned me, and I'm warning you now, be careful. Usually, in order to establish a power group, you need a new name. So you call what you are doing advanced material, or architectured materials, or optimized material, or metamaterial, smart material, synthesized material, multi-scale, multi-fix, complex. You find many of these flags. They are different names for the same thing. Okay? So, I like metamaterial, okay? But we must be aware that they are all the same. Also, mathematicians like to, so we are experts of generalized continua, But we are also experts of microstructured continua, continua with microstrains, continua with microstretches, higher gradient continua, Cossera continua, middling continua. They are all the same thing. They are continuum theories in which placement is not the only kinematic parameter which you need, and its gradient is not the only ingredient which you need for describing energy. So, in Napoli we say you must attach your donkey where the master wants. So if you are talking with somebody who claims that everything is continuous with microstretches, I advise you to say, yes, I agree. But in your mind, you must know what is happening. So you are not prisoner of the mental picture which somebody wants to give about reality. You look at reality itself. Okay? So it's a pity that Richard Tubin is too old, because otherwise we could have invited him here. Okay, so we have some mathematics and we have some physical phenomena, but we need a way for using this mathematics in order to describe this phenomena. We have a loud voice which is coming from the past. You should know, we have time, I don't know when I will be allowed another time to talk for all this time to people who are able to add vectors. My students now tell me that I am too mathematical. I have two vectors, I sum them quickly, without explaining what I'm doing. So I try to transmit to you what I am elaborating in these years, hoping to leave a trace. I also video record this for this reason. Okay. Gabriel Piola was the typical nobleman of Milan. He was belonging to a rich, very rich Spanish family. And for me it was difficult to get a chair in Rome, and I needed to fight many years. He declined a chair in Rome because he had no time to teach. He was managing his properties in Giussano, and in spare time he was giving seminars to interested people. I will tell you who are these interested people later. He developed his views about mechanics. So he wanted to find the equations describing the behavior of a continuum system. And he writes about this. Those who can read Italian will appreciate the extreme elegance of his Italian. And I must tell you that there was a poet in Milan, Monti, in that period, who said that the aim of the poet is to marvel people. Lo scopo dello poeta è la maraviglia. Okay, he is trying to impress us, and I was impressed. Since Lagrange managed to reduce all the questions of rational mechanics to the calculus of variations, look the rhetoric suspension now. The decision of insisting to avoid its use is similar to wish to behave as those who, being involved in the researches in higher geometry, instead of flying to use the formulas taken from integral and differential calculus, stubbornly persist in using in a pedestrian way the synthetic methods. So he claims that those who want to study continuum mechanics without variational principles are like those who, instead of using Cartesian coordinates, persist in using the Euclid constructions of geometry. Okay? He was proud enough, and he could organize that somebody at the end spent a lot of money for building a statue in the most important palace in Milano. And look, this book has a title, On a Controversial Principle of Analytical Mechanics by Lagrange. So already in 1856, the principle of virtual work was considered controversial. It will remain controversial for some psychological reasons, I think. Okay, these are usually one believes that the most recent reference is the most appropriate one. I think that in the theory of generalized continua, the books by Piola are the most advanced in the field. I have written a paper with Luca Placidi and Ugo Andreaus. We believe to have proven that the famous peridynamics, which is claimed to be developed in the United States now, is available already in the book by Piola. Okay. Of course, they are written in Italian. I know this is a problem. For this reason, the poor Luca was obliged with me to translate it in English, and now also Antonio Cazzani and other people are doing this work with me. Okay. Now, back to technical things. Okay, so it seems clear, because of what I said to you, that we will use the principle of virtual work as a fundamental tool. So I have a body, I have a sub-body, I have a placement of this sub-body, okay, then I need, follow this reasoning is not easy, I agree, okay? You have a body, you have a sub-body, you have a placement of this sub-body. Admissible placement, so a placement which you consider is allowed by the constraint applied to this sub-body. Then you must admit, and I think it is easy to admit this, that a family of C infinity small displacements starting from these actual configurations still give to you, summed with the first placement, another admissible placement. So we are assuming that a subset of C infinity test functions give you, when summed to our placement, another admissible placement. So you, if you are familiar with the nomenclature used by Lagrange, you accept that in the set of virtual displacements starting from a given actual configurations, you include all C infinity displacements. Okay? While in United States and in Italy, at least in those universities where everybody wanted to be American, people claimed that second gradient materials cannot exist. Paul Germain and Salançon à l'École Polytechnique were teaching this to students. This is a very astonishing feature of human knowledge. In some groups, you believe that something is impossible, and in another group, this impossible thing is taught to students. So when I met Pierre, I discovered the books by Paul Germain, then the books by Salançon, and I learned about the principle of virtual work applied to continuum mechanics. Because what is very strange is that in my university, finite dimensional systems were studied with the formalism of Lagrange. I never understood this. Until we studied finite dimensional systems, we used Lagrange formalism. When we started continuum mechanics, then I discovered that in a book, Truesdell wrote, finite dimensional systems can be studied with Lagrange formalism, while continuum mechanics needs another way of approaching. So, when somebody very clever has a wrong opinion, a group of people follows these ideas. Now, the fundamental ideas of Paul Germain and Salançon in these books are the following. We want to talk about the power expended on a virtual displacement. In the set of virtual displacements, you include C infinity fields. Okay. Are you ready to accept that power is linear in the displacements? Are you ready to say that if I change a little bit the virtual displacement, then the power is changing a little bit? So in mathematical words, are you ready to accept that power is linear and continuous in the set of Fréchet C infinity set of test functions? You know, I try to attract the sympathy of French people, pronouncing all French names. What can I do? Mathematical physics is strongly French in this period. Okay. So, if you are ready to do this, we can postulate the powers expended by the actions exerted on or exerted in a subbody B are distributions in the sense of Laurent-Schwarz, notwithstanding the name is French, concentrated on the boundary or on the body B. Okay? Now, technically speaking, I'm very proud to have studied this in my classes at the university. You have three representation theorems due to Laurent-Schwarz for distributions. The first one says that every distribution having a compact support can be represented as the sum of a finite number of derivatives of measures, all having their support included in K. To explain this technically, we could need some time if you do not know theory of distributions, but I will give you examples. Okay. There is another theorem which says that, no, this is a definition. Therefore, given a distribution, you have its order is the order of the highest derivative appearing in it. Okay? Then, when you have a distribution whose support is included in a regular embedded sub-manifold, then you can uniquely decompose it as a finite sum of transversal derivatives of extensions of distributions defined on the manifold. And this will play a central role. So, what a distribution on a surface is doing, it is testing all transverse derivatives of test functions. Okay? But I will give you formulas for this, because in Schwarz there is no this formula. Okay, so now we must take our time, but maybe I've changed my mind. We will go back here later. I want to give you a small detail about the geometry of this embedded manifold. This trick was used by Pierre for doing some calculations I wanted to do in another way. Then I discovered that the source is always Paul Germain. So take one surface or one line embedded in E3. You have for the line a tangent vector, for a surface a tangent plane. So you have a tangent space, but you also have an orthogonal space. For the line you have the orthogonal plane, and for the surface you have the orthogonal line. This is the reason for which I needed to talk about normals and tangents. Okay. So if you call capital P the projector in the tangent space of your embedded manifold, and if you call capital Q the projector in the normal space, of course P plus Q is the identity. Using Levi-Civita notation, the identity delta ij, for making the story easier, I introduce another reference which is always the same. It is a fixed reference to which I attribute the indices ij. There is also a strong controversial issue about the use of Levi-Civita notation. Soon we will need to handle nth order tensors. And I do not know any way for doing correct calculations on n order tensors without using Levi-Civita notation. I simply say that before changing the notation of Levi-Civita, we must reflect a lot to be sure that we are doing a good job. So I keep using Levi-Civita notation. By the way, in Paris, Lichnerowitz introduced this, and most likely the source of Paul Germain is Lichnerowitz's book. So delta ij is Pij plus Qij, then P is a projector, so P square is equal to P, Q is a projector, therefore Q square is equal to Q, and P and Q are orthogonal. Summation over repeated indices, Einstein notation is used, and we have contravariant and covariant representation. Okay. The fundamental tool we need to use is the divergence theorem on the manifold M. So you have a vector field W, you project it in the tangent space of M, you calculate its divergence, okay, which is defined in this way in coordinates, and this is equal to the integral on the boundary of M of the flux of W in the normal to the boundary direction tangent to the plane. This you can find in Spivak, but it is written in every book of differential geometry. I think you find it also in the entry of Wikipedia. I mean, it is something very well known, which you can even prove rather easily. Okay.
But can you say a few words on the regularity of fields and of the surface?
In this, I'm not so precise as I should be. I behave like the good mechanician. We assume that the fields are as regular as we need. Okay, Samuel, you are touching a very painful point. I think that, but Pierre sometimes agrees with me, sometimes disagrees. I think that you can do this in the sense of distributions, so with weak derivatives. But I'm not so sure, and actually we are doing it for C2 fields for the moment. Okay, so we are using rather regular surfaces and rather regular fields. Then we need to investigate where we can extend this. So your question is appropriate, and I was trying to hide the answer. Okay. Okay. This formula is very useful. If the field is not tangent, you can decompose it in the tangent plus orthogonal way, and using this formula, which comes from orthogonality of P and Q, you get this plus that term, okay? So at the end, you have the flux on the boundary and this term on the manifold. Everybody who has studied Laplace formula on a surface carrying an energy and a membranal stress knows that this formula is very useful, and the first addend gives you jump of pressure equal the curvature times surface tension. Okay. So now I will go back later to the integration by parts, because I want to arrive here. Maybe somebody should say me when I must stop for the coffee break. Okay. Now, please try to follow the line of thought which we are, without knowing, taken from Piola, because I discovered Piola after having elaborated this with Pierre. Okay. You know, when you have understood something, you find it much more easily in the books. This is the sad news. Okay. The internal power is the power which inside you are expanding inside a body for every virtual displacement. We said it is linear, we said it is continuous as a postulate. The theorem of Schwarz tells you that the dependence on V is given also in the weak sense by this formula. In the sense of distributions, this is the derivatives of T. You know, when you define the derivative of a distribution, the derivative of the distribution is the integral of the previous distribution applied to the derivatives of the test function. Okay? So, this animal, with suitable regularity assumptions about the stresses T lambda, is the most general distribution. So this animal is the most general internal power for the body B. This is the theorem, an application of the theorem of Schwarz. Now, we are familiar with this formula when T0 is 0 and n is equal to 1. Because everybody who has studied some continuum mechanics knows that the internal power is given by integral of T grad V, where V is the virtual displacement. So what mathematics is telling us? Mathematics is telling us the following. If power is linear and continuous, okay? If you don't want to assume anything else, you must be ready to introduce many Piola stress tensors. You will not manage to let me call them Piola-Kirchhoff, okay? Because Piola wrote them 25 years before. What is a Piola tensor? Is the dual in power of the gradient, first, second, lambda gradient of virtual velocity. So, even if you need to try to understand a complex mathematical structure, when you are inside, you are illuminated by its elegance. Your assumptions are very simple. And what you get jumping on you, that you have zero order stress, the dual of velocity. First order stress, the dual of gradient of velocity. Second gradient and gradient. All duals are all tensors. Which is the order of T lambda? Lambda. You need to saturate it with all partial derivatives of V. Okay? We have to stop. As a conclusion, what we can say, as a conclusion, we can say that stress, as described by Cauchy, is inadequate for describing the most general continuum. 10 minutes. We need to introduce many stresses. Now, digging in the literature, after having understood this, I discovered that another two losers in the battle, you don't have only Tupin, you have also Rivlin, Pipkin, Green, Nagdi. These are all variational people who were destroyed in the controversy about variational principles or balance laws. Okay? Green and Rivlin called these all L times contravariant tensors T lambda, lambda order multipolar stress. When I read this name, I said, I've seen it somewhere else. So I digged in Landau-Lifshitz, and I discovered that in electrodynamics of continuous body by Lifshitz, you find multipolar fields. So you have dipoles, quadrupoles of electric displacement, and their dual are multipolar tensors. So this is not a new idea, and Green and Rivlin are using it. Okay, so now I think to have given all ingredients for justifying next step. Which is next step? The principle of virtual work, the last postulation we need, says that the power of internal actions is equal to the power of external actions for every virtual displacement. So I want to try to explain you with words, then I will try to explain you with integration by parts, why this postulation is very important and very powerful as a conceptual tool. And I try to do it with an example. This example is given in the book by Piola. You know, if I were Bibliolatas, which was the owner of the director, one of the last directors of the Library of Alexandria, Bibliolatas in Greek means the man who forgets the books he has written. Because he wrote 4,000 books and is contradicting what he wrote in one book in another book. Okay? It is clear that he was appropriating the book of other people, and as he was the director and as he owned the only copy in the world of a book, he could easily change the name of the author. Okay? So if I were Bibliolatas, I could tell that this idea I had myself, but I should destroy all books by Piola, and there is a copy in Google Books, so I cannot destroy it easily. The idea is, the example is very easy. Consider a fluid, an Euler fluid. The Euler fluid has an energy, the formation energy, which depends only on mass density in the actual configuration. So you can calculate the first variation of internal energy and you get the power of internal energy. Then you can integrate by parts and you get admissible boundary conditions. And what you discover? You cannot exert external shear stress on fluids. So, given a continuum, given internal power, means deciding which kind of external action this continuum can sustain. Okay? So Piola, the poor Piola, when was attacked violently by Poisson and Cauchy about his book, says, you are ready to say that fluids are only sustaining shear? So why you are not ready to accept that first gradient continua are only able to sustain forces per unit area, and they cannot sustain forces per unit line and concentrated on points? So his idea is the following, and I will try to detail this for you. The idea is, we have a large class of continua. When you restrict and you call n, you say that n is equal to 1, you get a particular class of continua, Cauchy continua. I am not against Cauchy continua. I am against the idea that they are everything. Okay? There are more general continua. And what we need to do, we need to discover what can be applied to more general continua. And for understanding this, we have only one way. We take this formula, we integrate by parts it, throwing the derivative on the other side. So Samuel will need to accept that for T lambda you calculate lambda derivatives, lambda order derivatives. So the regularity of these stresses are not the same. And this is another difficult topic. And so you discover which kind of boundary conditions can be applied on a body. What is astonishing is that when I was young as you are, and with Pierre we came, this very strange, because Italians were attacking me and not attacking Pierre on this subject. I do not know. We spoke, we gave a talk. I spoke about something, he completed it, they attacked me. Maybe because I was competing for a professorship in Italy and Pierre was not. I don't know. Okay. This point is written clearly in Piola's book. Using the principle of virtual work, boundary conditions arrive naturally. You naturally get the correct boundary conditions.
To comment on that, because you said that you cannot apply, for instance, forces underlying the Cauchy continuum.
Yeah.
But point forces. But if you consider the Boussinesq problem or the Flamand problem, where you have forces underlying on an edge, you can consider it, and it means that as a distribution, the loading of the surface can be a distribution, and seen as a limit of some surface forces, but going to the...
But you have something which goes to infinity.
Yes, but I don't see really the point, because you are in the frame of distributions, so the applied forces can be distributions.
I agree with you, and this is in the realm of which kind of regularity assumption we can accept for T lambda.
Yeah, but when we are teaching Flamand's...
Yeah, I agree. Yeah, but what you have, if you have one edge and the applied force on the edge, there usually you have a singularity with logarithm.
In elasticity, but not in plasticity.
Okay, so in plasticity,
Here we have no concept.
wait a second, in plasticity you start introducing another descriptor or a change, energy hidden in some plastic deformations, so you are regularizing it somehow.
There is no constitutive assumption, this is purely representation.
Yeah, yeah.
And as soon as you accept some surface distribution of forces, you can take the limit, and at the limit you have some distribution where you are line forces.
I agree. This is inside the regularity assumptions acceptable for T lambda. If T lambda is a measure concentrated on a line, what you say can happen. So when I will give you the list of assumptions, I will assume that this animal is C. Sorry, what is happening there? No, the antenna which I use for Claude is ringing, but I switched off. So your point, I mean, you are right, and I try to explain in which sense it goes in this frame. When you choose the regularity of T lambda, what is this T lambda here? Is integral over the body of T lambda. So you have a function, a measure which is absolutely continuous with respect to Lebesgue measure in 3 dimensions. Okay? So you assume that your stress can be represented as a volume integral. You have in mind a situation in which your stress is not integral on a body, but integral on a line of material particles. Okay? So it is everything about the regularity of T lambda. Because, and then you are in troubles in integrating by parts.
Yeah, but then we should exclude from our course Boussinesq's problem.
No, why? Why? I think that it is a nominalistic problem we have in mind. You have something which is concentrated on a line. Okay, I try to tell you, Laplace formula is not in this frame if T lambda is regular, because you cannot have in this context energy concentrated on a surface, because the integral of this on a surface is equal to 0 if TB is absolutely continuous with respect to Lebesgue. Okay, in order to get Laplace formula, you need a thick layer, and your Laplace energy is got integrating along the thickness. So in a paper which we wrote with Pierre, I think it will appear in ARMA soon, we write explicitly that this case we exclude for technical reasons because we are not able to do the integration by parts. So I simply want to say that with first gradient continua, using something concentrated, you can do something more. Okay? Okay, so I think we have to stop for the coffee break. Okay?
I have another nasty question.
Yeah?
If you put back the last slide.
Which last? Because I changed completely.
That was the T lambda integral.
Yes, it is very far. Yeah, it is very far from here.
Very far.
But I will go back another time.
And you have it in mind.
We can write it here.
It was the internal, what you call the internal power.
Yes.
How do you see that it's internal power and not external power?
This is a vexata question. I can answer you quickly, then we will go in more details in this. I will use the technique of asking help to the authority of Piola. T lambda can be later introduced via a constitutive equation, and then it becomes internal if you ask that T lambda depends on the local value of some deformation measures. So this is a general frame, simply. I have a T lambda whatsoever, which is a field, and for the moment I don't ask why it is internal, how it is related via constitutive equations to deformations, and things like that.
So the important thing is, just by the form of this expression, you are not able to judge internal or external.
I agree completely. Okay. I agree completely. With Pierre, we discussed this many hours.
No,
I will suggest you to read, just to be nice with Pierre. There is a paper he wrote before meeting me in Compte rendu de l'Académie des Sciences, and he writes internal and external power exactly in the same form, and then it is distinguishing them via constitutive equations. Yeah, it is the idea of Paul Germain in any case. Okay. Okay, but we will go back to this. Okay, so I will answer in more detail to the question of Samuel, who is touching another touchy, crucial point. And please, everybody who has questions, please ask, and please oblige me later to give you all details. I mean, where to find, in which papers, all these things, and I will give you slides. So we will maybe establish a Dropbox and we will share the files. Okay? Okay. In the past, I was criticized for many reasons. One of which is that I'm too mathematical, and the other one is that I'm not enough mathematical. Okay. To say what it means that two test functions are close is a very delicate point which has been solved by Fréchet, who introduced the distance between two C infinity functions with so-called Fréchet metrics. It is not very difficult, but it is a way for saying that two functions are close if and only if all their derivatives are close. This is a crucial point. You can have two functions who are very close, but their derivatives are very far, one from the other. So one doing these reasonings, we need to control what happens up to the nth order derivative. So this is another touchy business. So I wrote here with respect to Fréchet topology for meaning this. If you want to know where to find these details, I will give you all details. I can even give you the PDF files if you like. Okay. So this postulate we accepted. These theorems we discussed. Okay. Now we must be patient. There is nothing difficult. If you are familiar with Levi-Civita notation, it is even immediate. My business is I have a manifold M. This manifold can be one of these three. We can have the whole body, we can have a surface, we can have a line. So M can be one of these three. Okay? And I have a nth order tensor T and the gradient of T. Okay, now I want to underline this. Usually, you know, when doing a presentation, you are too quick. In the papers, however, this is written in details. What is this capital V? Here it appears as a scalar. Okay? Why? Because we are interested only in the saturation of some indices with the indices of derivatives with respect to Lagrange configuration. So you have the Lagrange configuration here. You have capital X. Capital X is X1, X2, and X3. Okay? And the index I1, I2, In are n indices. I1 is going 1, 2, 3. I2, 1, 2, 3. So now you understand why the Italian side of this. Okay? This is the notation of Levi-Civita. I want to underline for you that it is not true that this is an index notation. Because with this notation, I can decide that I'm saturating this index with that index. Or I could place I1 in another place. I can talk about symmetries in the indices. The so-called direct notation, very American one, which is considered more elegant and effective than this one, is good only for second order tensors. When you have only two indices, then it works. When you have more than two indices, these people sometimes invent .13 for meaning that you are saturating the first index, the first argument of a linear function with the third argument of the linear function. So slowly they are rediscovering Levi-Civita notation. Okay, so let's use Levi-Civita notation. Okay, so this is the first observation. The second observation is that capital V could be any kind of tensor. Lagrangian, Eulerian, half Lagrangian, half Eulerian. So we could introduce some indices alpha 1, alpha 2, alpha k, beta 1, beta 2, beta h. Why I'm telling you this? In a generic microstructured generalized continuum, the kinematics is not only the position of a material particle. You could have a spin, a microstretch, a tensor describing something or something else. So you can have many, in a Coursera, you have a rotation. You could have directors indicating directions of some moving fibers. You can have everything which you need. This V can be a very complicated object. Okay, these indices we are not indicating. I remember a discussion we had via Skype with Pierre. If now here I write all extra indices, the formula, which is already a mess, will become not legible, okay? Not readable, okay? You must assume that V plus the indices I1, comma, I1, In, and this T, I1, In, okay, all the other indices are here and are saturated and are not relevant in what we are doing, because we are integrating by parts only with respect to the derivation which is indicated there. Okay? So this is not a particular case. This is the integration by parts which can be done in a generic continuum, having as a kinematic descriptor placement and everything else which you need. Okay?
Why don't you translate the contravariant and covariant indices that you left to know in which order you consider the form? Because you put E1 above alpha 1, but usually you put the blank there.
Yeah, but you know, the beauty of this notation is that this can be saturated only with that, and you have no doubt. You have a summation of a repeated indices.
I don't know if the form acts first on the vector or on the covector, because you don't say if it's T I1 on the top and
okay.
alpha then, or alpha I, or is it simply to simplify the notation?
Okay, okay. They told me you are repeating all the time to me that you are a practical engineer, then you ask me mathematical questions all the time. We have Riemannian tensors. So contravariant, covariant are transformed one into the other. So we are in the particular case in which you have an inner product, and so you can. Samuel, I didn't know you on the side of the mathematical formal person. I'm happy to discover. So the
when I become a Riemannian or a Euclidean,
yeah.
I put all the indices on the same.
I mean, you could even write this way.
Okay.
With the alpha at the top and at the bottom. Okay. Okay. So I'm happy that you are more precise than I am. Okay. I hope that young people are following these discussions. Otherwise, we give you details. But in any way, in all these things in the book of Salanson are clearly written. But what I want to send the message is, you have other indices which are saturated, and so all the story I'm showing you treats V as a scalar. Okay? So it is not a particular case, it's a general case, and we focus only on the indices which we are integrating by parts. Okay, now my target is to write this formula equal to something in which less derivatives appear. So here you have n derivatives, and I want something in which you have n minus 1 derivative. This is the target of what we are doing, technically speaking. I remember without Skype, I think this could not be written, because using screen sharing with Pierre, we have written this formula. This is not so difficult. Why? Because here you have 1, 1. You can call, you can introduce a delta. You can introduce delta 1 J1, and you get exactly the same. Then you decompose delta in P plus Q. Okay? And then painfully you use binomial formulas for grouping all P's and grouping all P's, all the P's at the end and all Q's on the left. One is made only of Q's. These are the transverse derivatives. So in the formula where you have all Q's here in this addend, okay, in the decomposition with delta, you have all Q's. Then you have alpha Q's and m minus alpha P's. Of course, you can commute these how many times? The times of the binomial coefficient Cn alpha. Okay? Now, remember that Ti1, I2, In is naturally totally symmetric because of the possibility of inversing the order of derivation. Okay? So, you can easily play with inversions of this order of derivations. So, how many coefficients do you have when you have placed alpha Q's and n minus alpha Q's? C alpha n. Okay? So, with this simple reasoning, it is clear that you have one addend which gives you total transverse derivatives. Then you have the tensor PT, which is a projector. Double P takes a tensor, nth order tensor, and it produces another nth order tensor using this formula. So the first index is saturated with Q. The alpha index is saturated with Q. Then you saturate with P. So it is ugly, but not complex. It is a stupid formula. But why we need formula 7? Because for integrating by parts on M, you need a projected tensor. You need a tensor with a P on the right side. I've shown you the formula. So this one cannot be integrated by parts. All the others can be integrated by parts. So you integrate by parts, you get the divergence of PT, which is one less order, so it is n minus 1 order, saturated with the gradient n minus 1 gradient of V, plus the boundary term. Okay, Claude Boudin said to me that I have the phantom of Piola. With Pierre we had written this paper before I discovered Piola. When I discovered Piola, I've seen him integrating by parts, so turning the pages, I was really worried that he had done everything. Okay, I can announce you that he left us something to do, that is estimating this term. He writes, it is trivial to get it and I cannot calculate it. So luckily for us, he found bulk equations, not boundary conditions. Okay, but it is clear he had no differential geometry. Okay, but I claim, and I will give you the reference, that indeed Piola is the beginner of the Italian school of differential geometry. Because Piola had a student, his name was Francesco Brioschi, the founder of Politecnico di Milano. Beltrami was the student of Brioschi. Bianchi was the student of Beltrami, and Levi Civita was the student of Bianchi. So actually, even if we have to dig carefully in the literature, I think that differential geometry is born because of continuum mechanics, or there is a push given also by continuum mechanics. Now, this formula is simple, but you need to iterate it n times, because you need to get rid of all derivatives integrating by parts. Okay, so before proceeding, I want to show you, this slide is a little bit provocative, in the sense that I have written the previous formula in so-called absolute notation. Okay, this is a little bit difficult to interpret if you are not seen the previous formula. So, the T grad n is equal to T orthogonal grad orthogonal. Then you have the surface divergence of the projector of T grad n minus 1 V, and then you have the flux of PT saturated in nu, but it is saturated with grad n minus 1 V. So the denotation div ms is the tensor having these components. The divergence of S is a tensor of order n minus 1, okay? And S orthogonal is this animal, the projection of S along the normal direction. The elegance of this approach, I tell it to myself that in this we were very elegant, is that we write one formula which is good for 3 embedded manifolds: the body itself, the surface, and the line. What is the orthogonal space of the body? Empty, or the zero vector, if you prefer. The orthogonal space of a surface is the orthogonal line. The orthogonal space of a line is a plane. You can have one point, the orthogonal point is the whole translation space, and the tangent is empty. So in one compact notation, you get all integration by parts which you may need. But you need to iterate this. So we have done it. Okay, here is another time we have spoken about the integration by parts. I have to improve further this animal. Now, before integrating by parts n times, I need to define divergence P0t equal t. The power alpha of div m p is this animal. So you apply div m, div m, div m alpha times. This I have found written in words in Piola. The poor man had no formulas, so he explained with words. Okay? And remark that
Let's not use the word divergence.
no, bicomponents. Samuel reading Piola.
What does he say words then for that? What kind of things?
Okay, if you want, I will show you, but the tensor is A, B, C, D, E, F, G, H. And then he painfully say, take the first component, derive with respect to the first. And the terrible thing is, for him, the components in Lagrange configurations are A, B, C. So for writing the divergence, he must write D capital A over D small a plus dB over dB plus dC over dC. The first line. But then dB over dA. I mean, you find formulas which are 20 pages long, which is the evidence that you need Levi-Civita notation for writing formulas. Okay? But if you are interested, I can give you, by the way, they are all deposited in Hull, the translation of Piola and my commentary. So you can reach easily via internet. Okay, now for every totally symmetric tensor T, you can prove by induction the following general formula of integration by parts. So what you have, look, it is not anything terrible. You take the tensor T, okay? We skipped here the index K for writing the formula in a better way, okay? So what you have to do, you take capital T, you calculate div MP K minus J times, J goes from 1 to K, so you have K minus 1, K minus 2, up to K0. You calculate the transverse component of this, and this is the dual of grad JV transverse. Okay? Then you have, these terms are written in Piola. You have minus 1 to the power K, because the integration by parts introduces 1 minus. So if you apply it K times, you get minus to the power K. Divergence MP K times T dual V integrated on the manifold, and on the boundary you get P, these divergences, T saturated with the normal, external normal, and this is the dual of grad LV. Now you can understand the technical difficulties we have. You have the volume B. You integrate by parts, what you get? You get this animal, which is not appearing if you have the volume because the orthogonal is 0. You get this animal dual V on the volume B, and then you have a boundary on the faces. Then you take your cube. On the face you have grad L, where L goes from 0 to K minus 1. So you have decreased the order of the gradient because you have decreased the dimension of the manifold. Okay? So you arrive up to L equal K minus 1. then you have to start again. Because you are on one phase, and you want to integrate by parts, forgetting transverse derivatives integrated on the surface, plus sounding on the edges. When you arrive on the edges, here you will get k minus 2, because you have integrated by parts another time. Then you are on an edge. You integrate by parts another time, and you fall on the wedges. Which will be the maximum gradient on the wedges? At k minus 3. So, what we do? We have integral of t grad k v. We integrate by parts one time, we get surface integrals, where you have the gradient k minus 1. You decompose in orthogonal part, tangent part. You integrate by parts the tangent part, you fall on the wedges, on the edges. You decompose orthogonal tangent part. You integrate by parts, and you get edges, wedges on points. So, even if technically it's not so easy, it is not anything complicated if one is patient to check the details. So this is the formula which Albrecht asked me, and I want now to tell, I said something correct but not precise enough to answer Samuel's question. We assume that T lambda is regular enough in a big enough region for performing the integration by parts I have shown you. Okay? In Boussinesq affair, T lambda is regular in the interior part of the body. Okay? So it is not overlapping. Yes?
Are we talking regular in the weak sense?
I think that this integration, we have done it with T lambda belonging to C lambda, so strong derivative. But I think that this can be done in the weak sense, even if I don't risk to say this too strongly.
Because in your, I asked that earlier, in maybe derived from power functionals, you could only tell that from Schwarz's theory, the representative
is a measure.
Are distributions.
Yes.
Which means we would have to work with mean. If at all we can work with something like mean derivative.
Yes, I agree completely. But we can start for the moment assuming that T lambda is of class C lambda in an open set including B. Of course, you can say we can do better. We must do better, okay? Yeah, but when you will see what we get as a result, you will tell me that we need this intermediate step before proceeding, because the formulas I will show you has to be still investigated. Okay. So, as I told you with words, you assume the principle of virtual powers, or if you prefer, power balance, as I said. Okay, so you assume that you are good enough, you can decide which is internal power, which is external power, and you can equate it. Okay. And then, lemma. I will give you more details about the actions appearing here, but let us start with this lemma. You integrate by parts every advent of the internal power, okay? This internal power has to be equal to the external power. So, you need to have the same structure of the internal power and the external power. So the process of integrating by parts we have shown you has proven what? On an n gradient continuum, which is regular up to the nth order gradient, with all t lambdas doing what good has to be assumed in order to integrate by parts. To this body you can apply a volume force, so the dual of the velocity, virtual velocity, and we are happy about this. We are familiar with this. Then you can apply a force per unit area, F0, which is the dual of V. Unfortunately, or fortunately for us, there are some new animals. Which is this animal? F delta. F delta is the dual of the delta transverse gradient of the virtual velocity. So this is a new animal, or at least an animal, an object with which we are not completely familiar. This action is expending power on transverse derivatives to the surface. So when you take a body, you consider a Cauchy cut, and you consider contact actions on this Cauchy cut, you must be ready to accept that the part of the body which you have removed is able to act on the subbody you have chosen via an action which is the dual of the transverse derivative of the virtual velocity. Following Paul Germain, when lambda is equal to 1, we call it double force. And following Green, Rivlin, Nagdi, when lambda is delta is 2, we call it triple force. So in general, F delta is a delta plus 1 force or action. Okay? Then you go to the, but remark, the integration by parts tells you that if you have an n gradient in the volume integral, on the boundary you can have only n minus 1 forces. Okay? Then you continue integrating by parts, you find a force per unit line, and up to n minus 2 dual of transverse gradients. Now, in a nice paper which I wrote with Pierre in 1995, really we wrote it in 1993, but it was accepted later and published even later. Paul Germain helped us in publishing a contre-inducer on this. We have proven a nice property. If you have edge forces, then you must have double forces. And we also characterized the set of continua where you have double forces and 0 edge forces. Okay? Which is a nice remark. So you can have particular case of second gradient materials in which you have double forces on surface without edge forces. But you cannot have edge forces without having double forces. Okay? And the argument we did is nice. I don't know, maybe Pierre will talk about this. Okay? Yes?
Sorry. There is something that I do not understand, because probably there can be something which is not clear. But you use it, that's the very last line, a definition of capital AB and capital WB, which looks similar. Is it correct or not?
Capital?
Calligraphic A, let's say. It's the very last line.
This one?
Yes.
This is SB.
No, yeah, the next line.
WB?
Yes.
Epsilon B?
Epsilon B is the support of the boundary of B. WB the support.
Okay, I won't, okay, maybe... okay, okay. Okay, there is a support of boundary of B. Cosa?
Wedge come body.
Ah, sì. Here you have three boundaries. You are right, you are right. Okay, but as you are asking me this, okay, thanks, help me to see formulas, because go back to the cube. One edge of the cube is the border or boundary of one face, but also the border of the other face. Okay, so I call the set of points in the curve, or for instance of the curve, epsilon B. Okay, but the boundary of B is this curve with one normal and the same curve with the other normal as a result of the integration by parts, because you arrive on the same curve two times integrating by parts both faces. So you need to distinguish the concept of boundary of the boundary and the concept of curve, which is the support of this boundary of the boundary. Okay?
Just a related question. As your set of wedges is a discrete set,
yes,
it will be a sum and not an integral, the last one.
Yes.
Okay.
I am using the abuse of notation okay, you can discuss with Pierre about this. Actually, I had written some.
The integration with respect to the discrete.
Okay.
And here we could add, now we can add new applied forces. For instance, I could apply forces on the lines which are not edges. Now you can do it now, so
yes.
It's not there. It's not there.
Okay.
And points,
Samuel.
points which are on the smooth.
Samuel.
Yeah, but this is very important.
I know, I know. Samuel, you were an applied engineer, you told me, a poor applied engineer. In order to have applied forces on a face, you need to concentrate there something.
Yeah, but I think it's not a problem, because you can consider an edge which has nothing, which is not an edge if you want it. I mean, if you take a line with a flat edge, this is possible to consider. So I can apply it.
Yeah, you have to check the formula. You get zero. Our model is not good enough for answering your question, because if you have one curve on a face, the formula which I produce for you gives zero there. You need that geometrical singularity for having forces per unit line. So the forces per unit line which you want require a more general T lambda another time.
But I understood the argument as in a Cauchy continuum you cannot apply point forces or line forces, you can apply surface forces.
Yeah.
So I would expect you use the higher order theory to apply such forces.
Yeah.
And now you tell me only on your edges and
the jump of the normal.
You can apply line forces only where normals are jumping. No, I mean, in this frame, with the assumptions we are doing, I am not only presenting results, I am also asking for help. Okay. Okay, but you are without pity. You hammer in every weak point. Okay. No, you are right, but you are right. The problem of finding the formalism for applying on a line which is in the regular phase is a problem which has to be investigated.
In that case, you can just use the formal procedure you were suggesting before, considering a self-response and then the link.
Yeah. Okay, but it is not. Yeah. Yeah.
Combining the two approaches, maybe you have a more general one.
I don't know.
It's not so obvious because these applied forces, some of them will come in the balance equation, especially the volume one or the balance of edges. So I don't know if the applied forces they will also rise.
Okay, you have to be careful because here there is a different number of balance in the bulk and on the boundary. So if you want to talk about balance of things, you have a different number on the boundary and in the volume.
These forces will enter the respective balance.
Yes.
And if you apply lines, force on smooth lines, on smooth spaces, I don't know if they will rise also in the balance.
I am afraid that Samuel, I don't know. I have some ideas, but I do not know how to answer to this. Of course, I could answer with a trick, in the sense that you apply force on one line, and the equilibrium will show you a jump of the normal. But it is a dirty trick. I'm not satisfied with this. Okay, so please accept this limited case, okay? And what you discover is that you have forces per unit line, forces concentrated on wedges, but also up to n minus n-1 dual of transverse gradient on surface, up to n-2 dual of gradient on edges, and on the wedges everything is orthogonal. So you have grad, the total grad there. So, and gradient regular continua. So mathematicians will stop criticizing. Okay? So continua in which stress is smooth enough and all this can be done. Okay. In this case, on surfaces showing jump of the normal having a finite number of edges and a finite number of wedges, okay, this continua can sustain on the edges and on the wedges forces, and on the faces you can apply higher order forces. Now, what is Cauchy representation theorem? Cauchy representation theorem is a way for representing these forces in terms of what? The geometry of the surface and the tensors capital T. Cauchy representation is very simple, because in first order continua you have bulk forces and surface forces only, and F boundary B0 can be easily calculated as T, which is not Cauchy but Piola stress, applied to N, because we are all Lagrangian, so this is all Lagrangian. Okay? So you get immediately the representation of stress. Now, historically, this was what was suggested by Piola, because the integration by parts in the first gradient case, he deduced like this. I think he was the first one deducing the integration by parts.
And like you told me yesterday with the rewind that Cauchy did that.
Cauchy did later. Okay, but
in 23.
He published something in 22, but it is not important, because I tell you why it is not important. Because Piola is finding the stress via the integration by parts. Cauchy, later, in parallel, we do not know, but he used the tetrahedron argument. Okay? Okay, I will tell you something about the tetrahedron argument later. Okay, but what is important is that with this argument, integration by parts, you get immediately that the force per unit line is stress applied to the normal. Okay, so you have two equivalent approaches, tetrahedron or integration by parts. Okay, so now I can announce you that in a delirium of omnipotence, when Pierre and myself were much younger, we decided that we had to do second gradient and more recently nth gradient theories starting from a tetrahedron argument, which is much more painful, but we did it. And we also wrote a paper for the Royal Society where we proved that also for nth gradient materials the two approaches are equivalent. So everybody should be happy that if you prefer tetrahedron argument, you can do the same. However,
if you use the tetrahedron argument, you must know in advance how the Neumann boundary conditions are. And Cauchy assumed them in a simple way for Cauchy continuum. But how can you assume them for gradient material where they become rather lengthy?
Albrecht, we wrote, I think, 40 pages about this. We give you the paper. If you want to read it, it is not yet published, but we rely on you, so maybe you find misprints. Okay, it is difficult, but you can generalize null theorem. You remember, null says that when you have a quasi-balanced something, then the contact action depends only on the normal. And then it proves in a linear way. So what we did, we assumed good things about external power, and we could prove this structure. It is painful, I agree with you. So quasi-balance of external power produces this structure, which is now a theorem. So, okay, I try to tell this better for younger students. You can decide, or younger scientists, you can decide. Either I postulate the structure of internal power, and I get, as a result, the structure of contact actions integrating by parts. Or you can painfully characterize somehow the structure of external actions. The idea of Cauchy is that external actions are given in terms of surface, for us integral on lines and on points. You assume that this is less or equal than a constant times the volume, because it is balanced by something expressed in terms of volume integrals, and from this you deduce the structure of contact actions, and we could do this, and we could prove this as a theorem, instead of, but not starting from integration by parts, but from quasi-balance of external power. But I will give more details about this in my next presentation. I have another one, right? Okay, so I give this detail to everybody who asks. Okay? I don't know what Pierre will do. Okay. So the promised representation, which is not so difficult but also not so easy. I need to introduce a boundary stress. It is not so complicated. You remember, when I did the integration by parts, I found first the dual of the total gradient, then I decomposed the gradient in the transverse and tangent part, and then I integrated by parts in the tangent part. Okay? So, the part dual to the transverse gradient we called force or double force or K+1 force, okay? And it is what I've called it here F0 or Fj. F0 is the dual of the velocity, Fj is the dual of gradient J transverse, okay? However, doing the calculations, we got the dual of the total gradient before decomposing it in the transverse and tangent part. So we called this surface stress, T boundary B, or edge stress. Okay? Why? Because in the formula which I'm presenting you, I need this intermediate object for writing them in a readable way. So, what we do? We take tau T lambda. We calculate the volume divergence. How many times? Lambda minus 1 minus L. Okay? Then we apply it to the normal and we sum over lambda. Lambda goes from L plus 1 to N. In this way you build this T boundary BL and you plug it here. This animal is what? Surface divergence of the surface projector at the power L. When you use n equal 2, you get standard boundary condition used by Paul Germain for second gradient materials. When n is equal to 3, you get middling contact actions. Now, this is the the tangent projector divergence on the surface. So what you get is that force per unit line in a second gradient material depends on the normal, which is written there, but also on the gradient of the normal of Cauchy-Cut. So you have that contact actions depend on the curvature of Cauchy-Cut. And when you have third gradient, contact actions depends on the gradient of the curvature. So, Cauchy postulate is in general not valid. Force per unit line do not depend only for unit surface, do not depend only on normals. They depend also on curvature, gradient of curvature, and so on, in regular points, which, by the way, has been accepted normally in the group of Tupin ideology or postulation. Okay. Okay. Next is given by the J action on the surface, which is built in a similar way. Then we have forces per unit line on the edge, and look, you have the projector P relative to the line, so I call it P lambda here. So painfully you reach the forces per concentrated on points, and forces concentrated on points are forces and stresses, because there is no transverse part there. Everything is transverse, there is no tangent part there. The big difficulty of these formulas is that they are recursive. However, you can get more general actions applied, not general enough for making Samuel happy, but more general than those usually applied. So what I will do now, yes, no.
Because of the
Which other paper I should write?
In this expression, regardless of the grade of the theory, so the M here,
yes,
we have always the same kind of applied force. It's clear because of the dimension of the space.
Yes.
And I wonder whether so it means that the higher order stresses, somehow, if they are not indeterminate at some stage or non-uniquely defined, because of the dimension of the space, simply, that we have only this loading condition.
No.
Should we, or naively, should we stop at
I think you have heard some considerations by Pierre Casal as transmitted in the French school by Henri Gouin, okay, which I think stopped me for a while. So thank for focusing on this. Higher order stresses intervene in this formula, increasing the order of forces applied on the surface. If you have a 7th order continuum, okay, T7 will appear in the dual of the 6th order transverse gradient of velocity. So even if you cannot go beyond points because your space is three-dimensional, you can increase the order of transverse derivatives. I remember that Henri Gouin was discussing with me about this, and I needed a lot of time for persuading him. So I think the source of this vision is due to Pierre Casal. So he decided that going beyond third gradient is useless.
So you are saying if we consider Dirichlet conditions,
yeah?
We will prescribe higher order derivatives of the velocity field?
You have to describe, you have to...
So I will briefly order,
yes.
But it will not be reflected in the number of equations for the Neumann condition.
No.
Because the Neumann condition are always the same number of equations.
I mean...
Because it's due to the forces we have, regardless of n. We have only these two slides that you...
No, but look, you have Fj. J can be 1, 2, up to the order... Okay, I have understood your point.
Number of conditions.
The number of conditions depends on n.
This I don't see in the...
No, maybe I'm wrong, but look.
The Neumann condition.
Look here. F boundary of B, J, L goes from J to N minus 1. So J can be 1, 2, 3, up to N minus 1. So you have many boundary conditions because you have the dual of the virtual velocity gradient transverse of order J, which are all independent. Okay?
So it's the same number.
The same number, as Piola says. This method gives you always exactly the number of boundary conditions which you need. No, he says which you need. He's not saying for uniqueness, which you need. Okay, so before leaving, I must show, okay, this, we have said all of this. Look, I've written here, J0 up to N minus 1. Okay? So it is exactly, maybe it is not completely true, should be N minus 3 here, N minus 1, N minus 2, N minus 3. Okay. As usual, mistyping. I will correct all this. Okay. Pierre de Fermat is always right. Okay. Now, before I stop, I must go back in the schizophrenic way, as before, to practical applications. Okay? So, this is a so-called secret bunch of fibers, which with Samuel we were even allowed to touch. You remember in Lyon? And they use this for making European airplanes the best in the world. Okay? Airbus is flying and it is made with composites in which these fibers are there. Okay? This is the experimental measurement. Okay? Now, you can use, say, first gradient theory. Of course, somebody, I am ready. Okay, this is second gradient theory. So what is happening with my first gradient picture? Madonna Santa, non ce la... Commetterò qualche omicidio. I will kill somebody tonight. No, I will phone and he will not get his degree. Okay, there should be here a movie with first gradient materials in which these wings, instead of going in this way, remain horizontal. So, when you use as a continuum model for this body first gradient continuum theory, whichever is the constitutive equation you use, the wings are not going up. The reason is that here in this contact you miss some boundary conditions and you never manage to have this behavior which is experimentally seen. Okay, we tried to understand, of course this is a black box animal. There is a microstructure of this. They told me it is secret. So I asked to a Polish friend to build for me this 3D specimen, and we have studied its elongation in this way, this is exactly the shape which the secret material from Airbus is producing. So, what is happening to this material? Okay, here we have some numerical simulations in twisting for this same material. Okay, so what is happening? This is another numerical simulation. Ma che diamine sta succedendo? Okay, I'm concluding this. It's outside of my control, this. Okay? You know, this is, sorry, I will not use more than 5 times, okay? This is the Forza del Destino. You know what is the Forza del Destino? It's an opera of Verdi, composed more or less when Piola was dying. And he wrote, I have already another work which is not short and which will continue the present one. And I strongly desire to be able to produce ulterior factual evidence of the stated assertion. The assertion is that principle of virtual work is the best. Okay? But whenever I will be able to conclude my work, and no matter how successful will be my own effort, I am strongly persuaded that time will give reason to the words with which I started this memoir. You know, in Italian is much better. Qualunque sia per essere il termine a cui riusciranno le mie fatiche, tengo per fermo che il tempo farà ragione alle parole con le quali diedi cominciamento a questa memoria. You know, he died immediately after this. This book is posthumous. I will look for the other simulation. Le premier mot de ce mémoire, tu veux l'avoir? Celle à propos du fait que si tu ne if you don't use calculus of variations, you are not able to do anything. The sad thing is that he died more or less my age, and he wrote this posthumous. A pupil of him wrote this posthumous. I don't know if any pupil of mine will publish anything posthumous which I've written. Okay, and this paper was forgotten. You know, this story of higher actions and this structure of continuum theory has been lost. Okay, we have some minutes, I think. If you are patient, I will show you the numerical simulations I wanted to show you. Ecco. So we have tried every nonlinear behavior. If you don't get out of first gradient materials, the behavior will be always this one, with the wings which are not going up. The reason is that the model is not rich enough for including the correct external actions. They used logarithmic. Now, I cannot tell you that everything you try, it doesn't work. Could be. But we did one trial with second gradient materials and we got exactly the correct behavior. Okay? So, I would like to conclude doing a kind of resume of the ideas I tried to transmit. But before, I want to underline that the devil is in the details. What I mean is that talking is interesting but totally useless if you have not a precise, algorithmic and mathematically and/or mathematically rigorous way of presenting your models. Okay? So, I claim what follows. When you have complex, microscopically complex systems in which you have high variations, Claude likes to call them sharp contrast between mechanical and geometrical properties, right? When you have this microscopic situation, of course, if you zoom in the composite I've shown you, which has the wings coming up, you could do a numerical simulation in which every carbon fiber is modeled with a Cauchy continuum. Then you must model the interaction between each fiber. And you need millions of finite elements. Of course, Ivan, who is working with me, managed to burn Diablo, the computer we had, not the engine. The cooling system was working perfectly. The friction of the hard disk consumed hard disk. Okay, because he needed, for the pantographic structure I've shown you, he needed 14 days of simulations. Okay? And time is not a crucial issue, because if you destroy every 14 days 3,000 euros of hard disk, you are in troubles. So please follow this reasoning. You choose a scale, one model is good. I don't want to say that Cauchy is not good. If you choose the right scale, Cauchy model is good. Of course, you can zoom and you could see one atom of carbon. Then you need quantum mechanics. Then you can zoom out and you can decide that a bunch of carbon fibers is a beam, and you can apply Timoshenko theory. Okay? And you are saving some time, but you are risking not to be able to describe every model. Then you can try to invent a reduced model, for instance, for pantographic plate, a bidimensional continuum model. I've shown you one simulation of twisting, and this is lasting few minutes. But you have to be very careful. In standard plate theory, you have no energy in the in-plane bending of material curves. So in the in-plane motion, you have a first gradient theory. You have a second gradient theory only for transverse displacement in plate theory. In order to describe pantographic structures with a reduced 2D model, you need second gradient in plane, second gradient. So what we have called geodesic bending energy. So you have a more sophisticated model, but more effective, and it is valid at macro level. Of course, with a macro model, you cannot describe what is happening to a carbon fiber. So, I claim that for every length scale and every class of phenomena, there is one, or more than one, but at least one suitable model, and one has to be able to choose the right model for the phenomena he wants to describe at that length scale. Continuum models must be adapted to the situation where one wants to attack the problem. Okay, I ride the bicycle with a colleague. His name is Mario Pulvirenti. He is a mathematical physicist, a little bit elder than me, and while climbing the long mountain street, 9 kilometers long, blood is not arriving well to the brain, we started the following philosophical discussion. You start with atoms. You do statistical mechanics and you find Boltzmann equations. Then you crazily work on them and you find Euler fluid equations. Then what you do? Discretize it with finite elements. We are doing something similar. I have a set of beams, discrete. I involved Claude, for instance, in an homogenization of it, or with Pierre we had pantographic structures and we homogenized this. Then we got continuum. Then I came to Catania and I said, Massimo, can you do isogeometric sounding for solving this second gradient continuum? So, while arriving at the top of the hill, we said, we are stupid. Why passing via a continuum model? Nobody knows. You know. Because continuum models are very good in catching global behavior. In a sense.
And you don't discretize the same problem.
Okay, but somebody could tell you, are you good enough to start with a discrete model, jump the continuum step, and find another discrete model which catches the general features of your discrete model? I mean, this is a question. Okay, if you have, no, I like this.
That use lattice Boltzmann, for example.
Yes.
The problem is that when you have the results, you have to have an interpretation of this. And what do you use for interpreting? The concept that is given by the continuum mechanics.
Yeah.
So it's it's not so you have the results, but you don't have the interpretation.
By the way, I told you that you are, without maybe knowing, because you do not know Italian, you are a follower of Piola. This is more or less what he writes about the importance of continuum models for describing fundamentally discrete systems. But this is an interesting open question, because somebody could tell, powerful computers. I place inside the equation for discrete systems, and that's it. I wait for reading the results. actually having a continuum model means having a key of interpretation of the global phenomena you have. Right?
Maybe I can ask something about computer results. It is very interesting for engineers because engineers they say that I have this problem, so I want the solution, and you have the answer. This is this value that you get. Okay, but if you need a scientific interpretation, you don't need numerical results. You need the structure of thinking this, and this is not given by the numerical results.
Claude.
This is not given by the lattice Boltzmann.
As I worked all my life.
This is another point that is very interesting to get continuum approach, even if you generalize the continuum approach, because it gives you some way to have an interpretation.
I tell you that I worked all my life in continuum models, so it could be telling that continuum models are useless means that everything I've written is useless. However, one should doubt about everything. Okay, one could say, write the Lagrangian of the discrete system, and you find a method for interpreting it, the general behavior. In any case, I don't know exactly why, but it is a fact. Okay, a set of springs with balls, okay, is understood much better if you write Laplace equations. So I think that at the end there is a truth somewhere in the process of continuization, finding a continuous regular field whose values in points in a lattice give you the displacement of the discrete system, is a trick which allows you to get some global behavior of the system. Okay, but I think this is a field which needs to be better investigated. Okay, so